Today's topic is liquids, and we're going to do the same thing with liquids that liquids. We're doing the same thing with liquids that we did in the first section. We're going to explain the behavior of liquid particles using the kinetic molecular theory. A liquid is a form of matter that has definite volume, but it does not have a definite shape. It takes the shape of its container. So we're going to use the kinetic molecular theory of matter to explain the properties of liquids. We're always going to be considering these two opposing forces, the arrangement of molecules and their kinetic energy versus the attractive forces between them. So let's look at the motion. As in a gas, the particles in a liquid are in constant motion. However, they are much closer together and lower in kinetic energy than the particles of a gas. So, because of this, the attractive forces between the particles in a liquid are more effective than those between the particles in a gas. Liquids are more ordered than gases because of the stronger intermolecular forces and the lower mobility of the liquid particles, but they're still less ordered than a solid. According to the kinetic molecular theory of liquids, the particles are not bound together in fixed positions like they are in a solid, but they move about constantly. And because they have the ability to move around, this is what classifies both gases and liquids as fluids. A fluid is any substance that can flow and therefore can take the shape of its container, which is why both gases and liquids don't have a definite shape. Most liquids, of course, naturally fall downhill because of gravity. However, some liquids can still flow in the other direction as well. For example, liquid helium near absolute zero has the ability to flow uphill. Kind of weird. At normal atmospheric pressure, most substances are thousands of times denser as liquids than as gases. The higher density is a result of the close arrangement of the liquid particles. Remember, a gas takes up 1,000 times more volume than the same substance as a liquid. So if you have a milliliter of liquid, it will take up a liter of volume as a gas. Between liquids and solids, however, there's only a 10% difference. When liquid water at 20 degrees is compressed by a pressure of 1,000 ATMs, that's 1,000 times greater than atmospheric pressure, the volume decreases by only 4%. So we say that liquids are relatively incompressible. So you can see the difference in the animation between the compression of a gas because of the KM theory. Number one, particles are tiny and relatively far apart from according to their size. So there's lots of room to squish them together. Liquids don't have that. They're pretty close together. In contrast, a gas under a pressure of 1,000 ATM would have about 1,000th of its volume at normal atmospheric pressure. Liquids are much less compressible than gases because liquid particles are closely packed together. And in addition, they can also transmit pressure equally in all directions. I'm not sure if you've studied fluid hydraulics yet, but the whole premise the whole premise behind how hydraulics works is because of this property. Liquids have the ability to transmit pressure. So I think it works like in car garages, those big things that they use to lift up the whole car. There's something that presses down and you have hydraulic fluid, and that pressure by pushing is transferred, and that's what pushes the car up. Don't ask me any more than that because that's like physics and whoosh, done. Along with gases, liquids also have the ability to diffuse and mix with other liquids. But of course, diffusion in liquids is much slower because the particles are closer together and they have less kinetic energy, so they are moving at a slower rate. But of course, like everything, if temperature is increased, diffusion increases. So if you look at this video, which one has a higher temperature? The one on the left or the one on the right? Now, if you go by just the rate of diffusion, you should already be telling yourself that the one on the left obviously is at a higher temperature than the one on the right. But another big clue is that the one on the right also has condensation on the outside, which means that that glass was cooled. And now you have warm air, warm water vapor in the air condensing on the side of the glass. So that's diffusion. One of the really cool properties of a liquid is surface tension. Surface tension is a force that leads to pull adjacent parts of a liquid surface together, decreasing the surface area to the smallest possible size. This is common to all liquids, but of course, because water has the addition of having what? Why is water different? I want you to think of one or maybe two words. Polarity or polar bonds. Because water is highly polar, of course, water is going to show an enormous amount of surface tension. Gonna go, here we go. So look at that surface tension. And finally, I have a little bit that joins with the bloop. Amazing. Bing. And the droplet gets smaller. That even bounced on the surface before completely disappearing. Surface tension. Surface tension results from the attractive forces between the particles of a liquid. The higher the force of attraction, the higher the surface tension, which is why I mentioned water, which I'm going to talk about now. You see that frog is actually using surface tension to completely just have a Jesus moment. So why? Water has a higher surface tension than most liquids because of the hydrogen bonds. Also, I'd like to point out the fact that you have to look at the boundary between the surface of the water and what is above water. So we know that water is polar. We know that air is non-polar, which means that all of the water molecules on the surface here are going to be pulling even harder and closer together and pulling downward against the non-polar air above the surface. So water molecules at the very surface can form hydrogen bonds with the other water molecules beneath them and beside them, but not with the molecules in the air above them. So as a result, the surface water molecules are drawn together and toward the body of the liquid, which creates the high surface tension. So that means that all of the tension is going all around, but just not in the air above it. Surface tension causes liquid droplets to take on a spherical shape because a sphere has the smallest possible surface area for a given volume. Now, one of the things that we'll learn in semester 2 is about plants. The surface of plants is covered with a waxy layer called, I can't write, cuticle. Okay, I said it's a waxy layer, and if you remember from bio last year, wax is a type of lipid which is non-polar. So polar water certainly doesn't want to have any kind of contact with anything non-polar, but if it must, it's going to take on a shape that has the smallest amount of surface area, which is a sphere. Another property of liquids is capillary action. Capillary action is the attraction of a surface of a liquid to the surface of a solid, and it's closely related to surface tension. I mentioned it probably in our original first online learning when I talked about cohesion and adhesion. Cohesion and adhesion together contribute to capillary action. A liquid will rise quite high in a very narrow tube if a strong attraction exists between the liquid molecules and the molecules that make up the surface of the tube. So what you see here is water literally crawling up the glass tube against the force of gravity due to capillary action. Capillary action, again, is a combination of both cohesion, the water attracted to itself, and adhesion, water attracted to the sides of the glass. This attraction tends to pull the liquid molecules upward along the surface against the pull of gravity, and it continues until the weight of the liquid balances with gravitational force. Now, evaporating is a type of vaporization. Vaporization is a general term for a liquid or solid changing to a gas. So evaporation, boiling, and sublimation would all be considered vaporization. It's just a different state changing into a gas. So evaporation is vaporization without heat. Boiling is vaporization with heat. So the process by which particles escape from the surface of a non-boiling liquid and enters the gas state is considered evaporation. Should have used a different GIF here because what you're seeing is actually boiling. Sorry. What you're seeing in this animation is sublimation. You have, oh no, sorry, oh, because I thought it was solid bromine, but it's liquid. So it is evaporation. Liquid bromine, and they have that thing that's wiggling around on the bottom is called a magnetic stir. It's basically a little tiny magnet, and you put it on top of a plate, which has a magnet in it, which then spins the little rod, and you can mix inside of a beaker that way. Right, so this is evaporation in real time. Although it looks kind of time-lapsey, that looks time-lapsey. So it probably doesn't happen this fast. A similar phenomenon occurs if you apply perfume to your wrist. Within seconds, you become aware of the perfume's fragrance, because the scent molecules evaporate from your skin and diffuse through the air to be detected by your nose. So how does evaporation actually occur? So technically we're gonna think about this at the molecular level. I want you to like zoom yourself in as if you were like another liquid molecule next to other liquid molecules in a liquid. So all of the liquid molecules are going to have different kinetic energies. If you have particles that have higher than average energies, are going to move faster. Some of those particles that have higher than average energies are going to be at the surface of the liquid. And then finally, it will reach a certain kinetic energy where it is available to escape into the gas state. But they have to have two things. One, they have to be near the surface. And two, they have to have a high enough kinetic energy to overcome the attractive forces that are holding the liquid together. That's why it's always a balance between kinetic energy and intermolecular force. Is evaporation important? You can see from the picture that obviously, yes, the whole reason why you sweat is because of the cooling effect it has on the skin. Why does it cool the skin? Because when you sweat, your sweat is 99% water. So when that water evaporates, it takes body heat with it. Now, boiling is different from evaporation because it's with the application of heat. When a liquid is cooled, the average kinetic energy of its particles decreases. If the energy is low enough, the attractive forces pull the particles into an even more orderly arrangement, and the substance becomes a solid in a process called freezing. Like I said, it's always a balance between kinetic energy and attractive force. It's always a fight. So if kinetic energy increases, that means you can overcome those attractive forces and you can escape into the gas phase or escape your fixed position to be able to move around, as in melting. Or if you cool things down and you slow down that kinetic energy and the attractive forces take over, it can hold your gas particles into a liquid during the process of condensation, or even a liquid into a solid in freezing.